Hello everyone, my name is Rakesh. I'm a postdoctoral fellow at University of Alberta. Today I'm going to talk about the development of next generation high entropy alloy through semi-autonomous deposition techniques for sustainable industry futures. The components used in several industry sectors such as energy, aerospace, and marine industries show surface degradation in the form of wear and corrosion. The traditional materials for these components have shown limited capability to address such degradation conditions. So, according to the National Association of Corrosion Engineers, reported that the overall cost of wear corrosion exceeds $139 billion in North America. Therefore, it is essential to address uh, extreme degradations by the use of advanced materials. High entropy alloys are basically a new class of advanced materials that comprise of higher more principal elements with cumulative fraction, unlike a traditional design concept that consists of one principal element, for example, iron and steel. So owing to this complex mixing, HE exhibits unique stable structures and immense properties. So in my project, I'm fabricating a new composition based on aluminum, cobalt, chromium, iron, moly HEA using cold spraying and flame spraying deposition techniques. So these fabricated HEAs will be evaluated for different microstructure and mechanical properties to compare the structure property correlations. And finally, the performance under abrasion will be evaluated of the HE coatings when compared with uh, traditional alloys and coatings as well. The HE feedstock in weight percentage I have shown here, and the micrograph shows that the particles are agglomerated with an average particles around 15 micrometer. And two deposition techniques will be utilized. One is the cold spray techniques, where the small unmelted particles are accelerated at high velocity to successfully impact the substrate, and it has a low temperature heat source. Where the flame spray, on the other hand, has a high temperature heat source where particle melts and molten particles are accelerated uh, towards the substrate, uh, causing coatings. The substrate used in this study is aluminum 5052 alloy. Abrasion studies for these coatings have been performed to understand the uh, coatings reliability under sliding and abrasion moment according to the ASTM G65 standards. Here is the results. So the scanning ultraviolet microscope shows that the cold spray exhibited significantly plastic deformed surface with the absence of cracks and pores, where the flame spray on the other hand shows numerous cracks and pores where the porosities are basically 1.7 volume percentage when compared to the cold spraying, and where the average coating thickness is around 421 micrometer. The X-ray diffraction study suggests that both the coating exhibited the BCC phases. Interestingly, the flame spray showed the presence of oxides, and the oxide formation is mainly attributed to the in-flight oxidation during spraying, which is not obvious for the cold spray HE. The weaker hardness study suggests that the flame spray exhibited a higher hardness, which is 40% better than the cold spraying. And the high hardness is basically due to the presence of oxides. And the comparative evaluation study suggests that the flame spray moly composition shows 1.5 times better than nickel-based atmospheric plasma spray. This is basically due to the presence of oxides and the formation of BCC phases for the moly-based flame spray composition. Abrasion results suggest that both the coatings exhibited better wear resistance compared to the substrate, where the flame spray shows 24% better than the cold spray HEA, which is basically due to the higher hardness of the foam. The comparative study shows that both the coatings shows 2 to 9 times better than the traditional materials and the thermospray tungsten carbide cobalt coatings, and more or less similar to that of cold spray hard carbide coatings. In conclusion, HE coatings has been successfully developed using cold spray and flame spray deposition techniques within optimized parameters. And the results shows that the flame spray exhibited presence of oxides that contributed to higher hardness, thereby the lower wear rate for the flame spray HE compared to the cold spray HE coating. In my future work, the detailed mechanical properties will be evaluated to understand the structural property correlations, which is essential for different industrial applications, and different typological performance under sliding wear, erosive wear, and corrosion will be conducted to understand the HE coatings when compared with the traditional alloy concept. And finally, friction processing, which is a thermomechanical processing used to tailor the microstructure of the coatings will be performed to eradicate all the microstructural inhomogeneities and to enhance the coating's reliability. So that's it. Thank you for listening my presentation. Have a wonderful day.